Perfect. So the as I've done this class for a number of years, and one thing I've noticed is when we do final projects, and normally what we do for final projects is I give you guys a small little DC motor, and you'll have some limit as to how much energy you can give that motor. So normally, which just means I normally say, oh, you have a limit of this number of batteries, this size, this number. Right? So I'll specify how much energy you can use to accomplish whatever task you get. And so normally the way those final projects work is I'll provide a DC motor, which is just a little metal cylinder with a little shaft coming out of it. You hook up to a battery and it causes the shaft to spin. And um, I limit how much energy you can apply to that, how many batteries you can apply to that. So that kind of limits what you can do. And I would see the task you do changes from semester to semester. Okay. So normally what we do is we do something where you're competing against other teams. You guys will be split up into random groups and you'll be competing against each other basically for bonus points, a small amount of bonus points at the end of the semester. So it's either some kind of a race or some kind of competition, and whoever wins that gets a bonus multiplier on their presentation score. Okay. Now, what I would normally see is groups would be struggling with or complaining about or just in general just unhappy with the performance of those motors. And that's fair. I mean, they are cheap little $1, $2 little tiny motors, and you don't have a lot of batteries, but teams would say, well, the motor just doesn't have enough power. Well, kind of. I've actually seen those motors, if they're geared right, break fishing line, like really good, strong fishing line. They actually are capable of doing quite a bit. You just might have to do a little bit slower. And so, and it's fine because as I got to listen to and we kind of work through, and I'm sure there's a very good chance nobody's really talked to you guys ever about gear ratios or what that means, or how do I adjust speed versus torque. And I thought, well, that's just a simple thing I can start working into what we would normally talk about at some point. Normally I've got an extra day or two in this class, and so that's something we can cover. Okay. I might have to pause this and adjust the lighting. It's a little washed out, but anyway, what I want to do, and I'm going to pause my recording here because I'm not going to have a YouTube video of projection of a YouTube video. That just seems silly. So, but I'm going to pause here and we'll pick back up. So, like I said, it's just a very simple, simple machines from Earth Pen. I mean, it's cheesy. I appreciate you guys pushing through that there. But like I said, he had some pretty nice graphics, animations. It's better than I thought. It was probably better than me just pointing to words on a screen, right? And like I said, it's a simple 4-minute video. We got quite a bit done there very quickly. So if you're watching here, you've got information. You can go find it. Okay. All right. Now, what do we want to do with it? Steve, why are we doing this? Well, a variety of reasons. There was one semester where some of my intro groups in the final projects, it was a bit of a challenge, the final project I gave them that semester, and one of my colleagues that came in and was kind of helping me evaluate the presentation said, do you talk to them about maybe the simple machines? And maybe that's a way they can generate some ideas. And I thought that's actually a pretty good idea. I'm already talking to, I already have this presentation where we talk about gear ratios and changing torque versus speed. And it's a wonderful place to do that. We don't have to spend real long, just say, hey, there are additional machines beyond the gears and pulleys that we're going to talk about that you can incorporate into your designs. Very simple. One of the challenges of the final projects is you're going to be limited on your budget, how much money you're going to be able to spend. Okay. Or at least how much money the final design can cost to be rebuilt is normally what I do. I normally say, you get like a $20, $30 budget. If we built like 100 of your 100 copies of your device, it needs to stay under this amount per device to rebuild those. Okay. So that's normally how we kind of enforce that budget, if you will. So with a very limited budget and a very limited amount of energy, you're going to be limited to pretty simple machines to be able to try to find solutions to whatever the project you end up with is. Okay, so I thought, yeah, that's actually a really good idea. Make sure we talk about what the simple machines are. All right, so I've got them written on the board here. They talked about it there in that video. I don't know why my PowerPoint's being really sluggish here. I don't have crazy animations. I have some animation. It's not crazy. I'm not sure. There we go. If we look at the simple machines, notice that you can kind of group these together. There's some overlap, right? The screws, as they mentioned, is a little more complex than the others, but it's still pretty simple in what it's doing. But you've got some of these machines are really kind of focused around rotation. And some of these machines are just simply applying or changing the direction of forces. And the screw is kind of a hybrid of both. It does a little bit of both there. But that's kind of how in my head I categorize those together. Okay. Now, what I want to do today is talk to you about gears and gear ratios, as I mentioned several times here. And gears are kind of like a specialized type of pulley. They're also very much like a lever. Right? It's kind of a combination between a lever and a pulley in that aspect. And to be able to talk about pulleys and gears and what they do for us as simple machines, we have to understand some basic physics here. And one of those physics concepts that we need to understand is this idea of torque. Right? So what is torque? Well, and you've probably heard this term before. This is the technical definition for torque. Torque is the tendency of an object to rotate as the result of a force being applied. Most of you are going to go on and take a course in statics. We often call this moment. So the moment of a force is how much that force could cause rotation if rotation is caused. Is there a technical difference? Normally, we reserve the term moment for when the object's not actually rotating, it's just the tendency to rotate. And then torque is often applied when the object is actually rotating. That's not a hard, fast law that you have to stick to. That's generally when we would use those different terms. You're perfectly okay to use either one, but definitely if it's rotating, we normally use the term torque. Torque is the product of force and the length of the lever arm. Now, what does that mean? Well, simple diagram here. Let's say we've got just a nut to be threaded onto a bolt, and I've got a wrench here. Okay. All right. Now, what happens if I need this bolt or this nut to turn onto a bolt? Do I put my hand here?
No.
Why not?
Because you're minimizing distance from the object you're trying to apply force to.
Absolutely. Right. I'm not going to get enough torque here because your torque, which we would normally use the Greek letter tau as a common thing we would use, capital tau. Your torque is basically going to be your force times, I'm going to call it L, being the lever arm. Okay. So, and that L is going to be the distance between your point of rotation and where you apply the force. Now, if I don't know what I'm doing, and I apply my force this way,
There's no moment.
right? There's no moment. Well, why? Right? If I apply force here, why is there no torque?
Because it's going through the center of the point, the origin point.
There's no rotation. It's going through. Notice what the distance between what we call the line of action for the force is and the point of rotation. If I apply force this way, that force passes right through the point of rotation. So there's not actually any lever on. There's not actually distance between that force and the point of rotation. So that means there's no torque being generated. There is actually, there will be torque this way. I can kind of lay the bolt over, right? That's not going to help anybody. So yeah, so that's not what we do. We don't apply the force out here. Okay. Now, what if I apply force this way?
Both side and side.
Right? It's force is what we call a vector quantity. Now it's beyond what we have to talk about here. But what that means, if I've got a vector quantity is something where the direction is also important. Not just the amount, but the direction is important. Torque is technically a vector also. Its direction is actually perpendicular to the plane it's being applied. And again, that's really way beyond what we need to talk about here. You guys are going to get there as engineers, but the direction of the force is important. So as it's written here, as I've written it here, this is assuming both force and the lever arm are perpendicular to each other. Okay. So this is the L represents the perpendicular distance between the direction of the force and the point of rotation. Anybody heard the term a cheater bar? What's a cheater bar?
It's a breaker bar. You stick
Breaker
with
bar,
it.
yeah.
Yeah.
This does not work, yeah.
Yeah. So if I take my vehicle in and have the oil change somewhere and, you know, they use the air impact wrench to really put that drain plug on there. You got to get that off later because, you know, I didn't have time to change it myself last time. Somebody put it on way too much. Yeah, cheater bars where you put something over the end of that wrench and you come out here and you can apply your force a little bit further out. Okay. So what you do is you increase your L. So there's a couple things you can do to increase torque. That you can see it's a function of two parameters, right? I can apply more force, or I can apply it over a longer distance. In either case, that will generate more torque, more likely to rotate. Okay. So we have to understand torque, or at least have a basic understanding of torque to really talk effectively about gear ratios and what they do. The other thing we have to understand is what we call rotational speed. Almost always, we're going to use a lowercase omega. It's not a W, it's a lowercase omega, Greek letter. Capital omega kind of looks like, if you've ever seen the symbol for ohms, that's a capital omega. This is a lowercase omega. Lowercase omega, that is rotational speed. Is the speed at or the rate at which an object is rotating. In your car, if you have what's called a tachometer, that's measuring how fast is your engine output shaft rotating, and that's measured in rotations per minute. Okay. We talked about on the video with the guy with the Stirling engine. I said that you watched it was going and then it goes back this way. That's because of the effect of the video camera taking it probably 60 frames per second, about 3,600 RPMs or 60 frames per, 60 rotations per second. The camera actually, it looked like it paused on the camera and went back the other way. That's because he got it up to a pretty good rotational speed. So those are the two main quantities we've got to understand when we're describing rotation of an object and what gears can actually do for us. Gears or pulleys can do for us. Now, if we look at a couple of gears rotating together. So when two objects rotate together, in this case, we'll say two gears, when two gears rotate together, the force applied at the teeth of those gears or the edge of the pulleys is going to be the same. This is our good friend, Sir Isaac Newton. This is Newton's third law. Action, reaction. For every action, there's an equal and opposite reaction. So if I've got two teeth on the edge of this gear, right? Two teeth on the edge of this gear, and one comes in contact with the other and pushes the other one. So long as this tooth doesn't pass directly through this tooth, they're applying an equal and opposite force. If they don't, they fuse together. They become one, which doesn't happen, right? At least not in our universe, to the best of our knowledge. Unless you melt one, then things are weird. That's a much more complex thing. So if I call this gear A, I'm going to use that blue. That's probably going to show up on the screen. If I call this one on the left gear A, I call this one on the right gear B. What I'm saying is that the right here where the teeth come in contact, the force, if gear A is being rotated, we'll say clockwise, the force as it comes around and rotates clockwise, the force that gear A is going to apply on gear B and cause gear B to rotate counterclockwise. That's going to be equal and opposite of the force that gear B applies. What does that mean then? Well, remember earlier we said that torque is equal to force times the lever arm distance. So if I've got a motor hooked up to gear A, that motor is going to apply a torque to gear A. Okay. So I'm applying a torque to gear A to cause it to rotate. What do you think the lever arm is out here for this force A?
Radius.
The radius. Because it's that lever arm is the distance from the point of rotation. So the center of that gear there, from that center out to that point, you've got radius of A. So the torque of gear A is going to equal the force of gear A times the radius of gear A. And I can say the same thing about gear B. But what I've got here, notice I've said, well, force A is equal to force B. So that means I'm going to solve this for force. So we're going to do some algebra today. Hope that's okay with you guys. Force on gear A, or the force of tooth on the gear A onto gear B, is going to be the torque of gear A divided by the radius of A. Simple algebra. And we've already said that those forces are equal and opposite. So force on A is equal to force on B. Therefore, that means the torque on gear A divided by the radius of gear A is going to equal the torque on gear B divided by the radius of B. Now, what I probably want to do, as we mentioned, is if I'm hooking up a motor to gear A to apply torque to it to get it to spin, I probably want to know, based on the torque I'm applying to A, how much torque am I getting to B? That's probably what I want. So I'm going to solve for torque B. Torque B is going to equal, I'm going to group the radii together. So it's going to be radius of B divided by radius of A times torque of A. Solve this, torque B. There we go. So what does that mean? Well, that means that if radius of B is greater than the radius of A, what do we know about torque B compared to torque A? Which one's bigger?
Torque B.
Torque B. If radius B is bigger than radius A, that means that the torque on gear B is going to be greater than torque on gear A. So we might look at this and say, wow, I mean, I probably want more torque. Why not just always do this? Just always hook a small gear up to a big gear. I'm always going to get more torque.
Slow step as well.
You don't have fast cars like that.
Yeah. It's a balance. What's the first law of thermodynamics? We talked about that last time. Energy cannot be created nor destroyed. What are these gears doing? These gears ultimately are just transmitting energy. I'm putting energy into gear A, and that's transmitting energy to gear B. And the first law says that energy cannot be created nor destroyed. It can only change forms. The second law says entropy must be generated, meaning heat's being generated as these two touch each other, and nothing's 100% efficient. So even as efficient as gears are, they're amazingly efficient. They're not 100% efficient. You're losing energy somewhere, okay, to something. But all I'd say, again, energy cannot be created nor destroyed. It can only change forms, meaning that I can't just magically have more energy in gear B. There's a trade-off. If I have more torque, it means I'm doing it slower. I can't transmit more energy. So the main two things that are going to drive energy in this transmission process is going to be torque and speed. Right? So if I have more torque, I'm going to end up with less speed, and that's what we see next. So if we talk about the speed, so again, I've got gear A on the left here, gear B on the right. If gear A is rotating clockwise, then gear B must be rotating counterclockwise. And we'll say that gear A is rotating at a rotational speed, omega A. And we'll say gear B is rotating at a speed, omega B. Now, we already mentioned earlier that those two teeth are not passing through each other, right? That doesn't make sense. They're pushing on each other. So Newton's third law says there's equal and opposite forces, equal and opposite reaction. But because they're not passing through each other, it means they're moving at the same speed. Right? The linear speed of those two teeth, they have to be the same. The rotational speed of the gears will end up being different. And that's what we want to know is how different are they? Because what we know is just because of the limits of physics that the speed, I'm going to use V, that's in physics, we use the magnitude of velocity to describe speed. So I'm going to use V for velocity. The speed of a tooth on gear A is going to be the same as the speed of a tooth on gear B. They have to be. They're not passing through each other. They physically have to be the same if they're traveling together. So if that's true, how do we find the speed? Again, we're saying that the speed of A is equal to the speed of B. And how would we find this speed? Well, if I know the rate at which it's being rotated, okay? And this is just a circle. Again, this has got radius A and radius B. How can we figure out how far one of these teeth travels in one rotation? What do we call that? It's the circumference, right? These gears are circles, they're traveling, or at least the teeth are traveling in a circle. So the circumference of that circle is 2 pi r, right? Circumference is 2 pi r. And it's traveling 2 pi r per rotation. Per rotation. Well, omega is rotation per time. So basically what I'm saying is if I take, this is how many times, this is how far it travels per rotation, and I multiply that by rotations per time, I get distance per time, right? I get distance per time. So the speed of a tooth on gear A is basically going to be the circumference of the circle times the rate at which it's going through that circumference each time. Okay, so this becomes then 2 pi r a omega a. That is the speed that the tooth is traveling out there. And it would be the same for gear B. So what I can do is I can say, well, since the speeds are equal to each other, I can say that 2 pi r a omega a, that is the speed of a tooth on gear A, BA, is going to equal 2 pi r b omega b, the speed of a tooth on gear B. And they have to be the same because they're not passing through each other. Beautiful. Now, let's do something similar to what we did with the torque. Let's say I'm hooking up a motor on gear A, and I want to know how does that cause gear B to rotate? I want to describe the behavior of gear B. Well, notice I've got 2 pi on both sides of this equation. That's not 0, so I can divide by 2 pi and be just fine. So I've got RA omega A is equal to RB omega B, and the mathematicians are still happy. And again, if I'm hooking up a gear, or if I'm hooking up a motor to gear A, and I want to see what am I getting out of gear B, I'm going to solve for omega B. That means omega B, and I'm going to group the radii together. So that means I'm going to put RA over RB times omega A. And you can see what's happened here, right? So if I write that over here, so we record it, omega B is equal to RA over RB omega A. So if RB is greater than RA, well, now I'm multiplying by something that's less than 1. That means that omega B is going to be less than omega A. And vice versa is also true, right? If RB is the smaller one, then I'm going to get less torque, but I'm going to get more speed. Again, energy must be conserved. We're just transmitting energy. We've got a complex gear set here. I'll put it on the camera so people at home can see it. All right, so what I've got there is, these are just 3D printed gears. This second one here is a complex gear. It's got a small gear on one side. All right, it's got a small gear on one side and then a bigger gear on the other. So when you put it in here, that small gear interfaces with this big gear. All right, so this big gear turns the small gear, which is on the back side. You can't see it from here. And that small gear causes both these gears on basically one pulley then to rotate together. And so what happens then is this big gear rotates slow, but look at this little guy here. He's going super fast. Okay, that's because this littler gear on here has to rotate faster to keep up with the speed on this big gear as it goes around. So that means this guy's going fast. And because this one's going fast, that means this bigger gear that it's hooked to is going fast, which means this smaller gear still has to go really fast to keep up with this big gear that's moving fast, because this big gear is keeping up with the little gear that is moving fast because this big gear is not. Right? Now, the cool thing about this then is the torque. So if I put my finger on this, it is almost impossible to move this big gear because the torque is transmitting back in the opposite direction, right? And with the opposite ratios. And the same thing if I put my finger out here to try to stop this thing from rotating, but if I put any amount of force basically on that little gear, it'll actually get this big gear to move because of the way the torque's getting multiplied back. So I'm getting speed one way, torque back the other. Okay. So why do I do this? Why am I talking about this? Again, the goal here is when you guys when you get motors for your final project, and they're cheap little motors, and we're not putting a whole lot of battery juice to them. Okay. So you can actually get a lot of torque You're just going to have to be creative about how you get that. Now you can use gears. I will tell you on a low budget, gears have to line up perfectly, right? And if I'm hooking those up in cardboard or soft wood because that's what's cheap, that they may or may not, and you throw them in your car to bring them here, and then you throw them, take them back home to work on some more, and you bring them back and forth. Over time, I've seen groups do really good with gears, and I've seen groups the gears don't mesh because a slight shift in your cheap design doesn't hold up. So one thing to think about then is so gear ratios, we've already written those on the board. That I've got a blank slide to make sure I put these here. Let's talk about something that's a little more forgiving than gears, but works much the same way. And that was one of our simple machines, is the idea of a pulley. So for me, I would put pulleys and gears basically together, and both of these are basically based on what we just talked about. I would submit to you, these are rotating levers, right? These are rotating levers that where with a lever, I can increase basically the torque, if you will, how much I can, I can use a small force over a much longer distance to get the same effect on the other side. That's how a lever works. And that's basically what we're doing here. We're saying, if I change or modify the distance which this force or torque is being applied, I can get more or less torque on the other side. So again, I view in that aspect, I view gears and pulleys basically as rotating levers, right? And the advantage of pulleys over gears is you don't have teeth that have to be perfectly aligned. You just got to keep a belt on there, and it has to not slip, and that becomes your challenge. Is it not going to slip, or can it hold tight enough to actually work? But that's so it has its own challenges. One neat thing is, remember in the gears how one rotates clockwise, one rotates counterclockwise to oppose each other. With pulleys, they're going to rotate the same direction. Okay, so the two are going to rotate the same direction, but the same basic principles apply. The force applied through the belt is essentially the same throughout. It's the same belt traveling across here. So it means it holds the same tension at all points, roughly. It's not exact. You'll have a slack side, so basically this as it's rotating here, this side will loosen up a bit. And this side down here will tighten up in a real belt, because all real belts are going to stretch a little bit. Okay. But if you get it nice and tight and you don't have too much and you don't have any slippage, this works just fine. Okay. Again, there are some unique challenges to gears and there's some unique challenges to pulleys, but as far as the ratios, they work the exact same way. Okay. If I need more torque, then I need to adjust my pulley size accordingly. So the bigger the radius of one pulley, so if radius of pulley B is greater than the radius of A, I'm going to get more torque on pulley B, but it's going to go slow and vice versa. Okay. And you can see that in this graphic here. This smaller one is rotating faster to keep up with the big one because it's the same pulley or it's the same belt or string going around it. That's the molecules of the string can't pass through each other, so they all have to move at the ssame speed. So that means when it gets to the second pulley, they've got to be moving at the same speed. Okay, so the speed at the surface of the pulley is going to be the same, and so that means that you get this difference in your rotation. If one's bigger than the other, then the bigger one has to rotate slower to stay at the same speed as the smaller one. And if you ever walk beside somebody that has shorter or longer legs than you do, you get this principle, right? They've got if you walk next to somebody that's got shorter legs, they've got to walk twice as fast to keep up with you with your long legs. It's the same principle. If I've got a small gear or a small pulley, it's got to rotate faster to keep up with the big one that it's hooked to. Okay. This is kind of I just found some simple GIFs here, and so this is a complex combination of gears and pulleys. This is a planetary system here. But so you can kind of get the basic idea here of what they're showing. So anyway, just give you some ideas to think about as you get your challenge for your final projects here in a couple of weeks. Again, we'll start those. We've got some guest speakers in the midterm, and then after that, Beginning of it or early April. I normally try to do about 10 class periods, so we're going to be right at that. So, okay. Questions, comments, complaints from me? Cool.